welcome to the course UEC 001. We are starting the module with diode equivalent circuits. So let's start with the definition of diode equivalent circuit. And the definition says that diode equivalent circuit is a combination of elements which is selected for a device in a particular operating region. Okay, so the category number one, it is piecewise linear equivalent circuit. Piecewise linear equivalent circuit. So in this, we will select a particular model where we will see the contribution of each and every component to form a circuit. The VI characteristics which we have plotted earlier. It seems like this is the curve. We are mostly interested in the forward bias region. This is my ID in terms of milliampere, VD, volts. So if you can check, this was my knee voltage VK I have represented, reverse bias case, forward bias case, and you can check as it is a bit slopey, so I can say that there will be some average resistance. Our average we can mark. We have studied in previous session the different resistances of diode. So what is the requirement? Like, as we are dealing with the diode, so this is the symbol of diode and representing suppose with D, ideal diode. So what are the components involved over here? Now for the simplicity, I am taking the example that I want to prepare the model for a diode manufactured from silicon. So in this model, the first component will be diode itself. So it is my ideal diode. The second thing is there should be a battery VK. As you can check, I have marked over here silicon, so a typical value will be of 0.7 volts. Then the third one is the line curve is not exactly vertical. That means there will be involvement of resistance, and in order to handle large swing of AC signal, I am writing over here R average. So in most of the situation, the typical value of resistance is very low. I am considering a particular value of 10 ohm. So this is my linear piecewise model of diode. This is linear piecewise model of diode where we have involved each and every component. Ideal diode we have taken from the material, like we have taken the silicon, so battery of 0.7 volt, and we have included the resistance also. In some applications, the value of resistance can be ignored as it is very low. So if we want to do that particular thing, then we will have the model, and that particular model is termed as simplified equivalent circuit. So now I am having a simplified equivalent circuit, and let me draw the waveform first so that we can get the idea. So as our aim is to remove the contribution of resistance, so this will be the curve. For better understanding, I have just drawn this line to the above side. The remaining things are same. This is my ID in terms of milliampere, VD, volts, the zero level, and now you can check from here, value of R average will be 0 ohm as it is having a vertical line, but Vk is still there considering the previous case of silicon, so it should be 0.7 volt. That means this is my reverse bias condition and this is my forward bias condition, and you can see the significant difference between the two characteristics. This was the characteristics for piecewise linear equivalent circuit, and in the simplified equivalent circuit just we have kept only one thing, and which is my average resistance is 0. So now what will be the model? In the model the several parts are, first is diode, ideal diode should be as it is, and second thing is battery involved is there. So now you can check in this particular model one component has been removed, that is the average resistance, and this is removed because it is now replaced by a short circuit. So now you can check, this is my ideal diode, Vk considering the same example, so 0.7 volt, and this is my simplified equivalent circuit. Now the final category for this is, which is the third one case, and in most of the numerical directly it will be used, and this is the ideal circuit. So as the name suggests, ideal circuit means in this particular component value of R average equals to 0 ohm and Vk will also be 0 volts. So if I am considering these two, so first you can see the curve, and as far as the curve concerned, we have already seen the curve for ideal diode. This will be the curve. Red color line is the curve for ideal diode over here. This was my ID in milliamperes, VD in volts, forward bias region, reverse bias region, no bias region. So you can check here, R average equals to 0 ohm and Vk is also 0 volts. So as far as the equivalent model concerned, very simple model, only one diode is available, battery is replaced by short circuit, resistance is also replaced by a short circuit. So this is simply an ideal diode. So these are the three models importantly used. In most of the cases, if nothing is given, so we can directly prefer with this because this is the simplest form. Okay, in this, neglect the value of resistance and neglect the value of uh, knee voltage Vk. So what is the importance and what is the requirement of this particular article is, you can check every semiconductor device is sensitive to the frequency. Every semiconductor device is sensitive to the frequency. That means there will be involvement of stray capacitance for the diode. So one can easily understand if I am replacing the term Xc. If I am just saying that Xc equals to 1 upon 2 pi f into c. Now for lower to medium range frequency, I'm considering to the lower range, what will happen if f equals to 0, You can just see over here, if f equals to 0, xc will be infinite. So xc means infinite. It seems like a open circuit. It will not have too much of impact, but on the other side, if I am considering higher frequency term, that means say f equals to infinity, then you can check value of xc is 0. That means the behavior of capacitance is short of short circuit. So there may be a chance that at higher frequency, the frequency response of the circuit can be changed. Okay, so one cannot neglect the effect of diode capacitance. So we must study the diode capacitance. So basically, two types of diode capacitances are available over here. As we have seen in the working, diode work in forward bias and reverse bias condition. So in forward bias case, the diode capacitance is termed as diffusion or storage capacitance, and for reverse bias it is termed as transition or depletion capacitance. In fact, the idea of reverse bias can be directly explained with a high school level course, one relation C equals to epsilon A by D. If you can recall, it is for parallel plate capacitor, very common formula where epsilon representing the permittivity between the two plates, which is showing the isolation component, and A is the cross sectional area of the parallel plate, and D is signifying the distance between the two plates. So this is a very common formula. On the basis of this we will understand. So if you can refer, you can just see on the right hand side I have drawn three schematic. First is representing the no bias condition, second is forward bias condition, and the third one is reverse bias condition. And I have marked the three term, that for better understanding I am rewriting omega, omega f, and omega r. So with the notation one can easily understand with their meaning. So omega is representing the width of depletion region. For no biasing case, omega f is representing the width of depletion region for forward bias case, and omega r is representing depletion region for reverse bias case. And you must be clear with the fundamental term which we have already covered, that omega f is less than omega, and this omega is less than omega r. So when diode is reverse biased, depletion width is increases. So among the three, this omega r should be highest and omega f should be lowest. So you can check. I want to simply show you the final curve for capacitance, and this is the general curve. Here I am having capacitance on this scale voltage, and basically for diode concern you can just remember this is reverse bias for the negative voltages side, and this is my forward bias case for the positive voltages of side. As I have mentioned over here, diffusion capacitance and storage capacitance will be the part of forward bias. Transition capacitance, depletion capacitance will be the part of this reverse bias. Now, what the analogy is, you can check from here, from the third category. Under reverse bias condition, the value of omega r is highest. So, in this particular relation, you can check uh, C is proportional to 1 by D, because in reverse bias case this epsilon is representing as because there is no carrier in the depletion width, only immobile ions are there, so it forms like a isolation case, so epsilon will work over here. And as I am increasing the voltage, so as I am increasing the voltage means I am increasing the voltage in negative direction, so what will happen, this omega increases. So you can see that omega increases. In this formula we have used D. So if I am saying that voltage increasing, so correspondingly what will happen, the value of omega R is also increasing. So if omega is increasing, that means C will be decreasing. The capacitance will decrease. And you can see in the curve. So over here, I am mentioning CT, that is my transition capacitance using the initial word in the reverse direction. However, on the forward direction, a similar sort of explanation can be taken on behalf of WF. If you are increasing the value of voltage, but in this direction, I am talking about voltage in positive direction. So if I am increasing this voltage, that means the value of this omega f decreases. Space charge region is decreases just because of forward bias region. And here I am correlating this with C. So ultimately my capacitance has to be increased, and which I have marked over here with CD, that is my diffusion capacitance. So my overall capacitance, the total capacitance, if I am interested to find the total capacitance, C total. So this C total becomes CT plus CD, but you can see that the dominating component is CD, so somewhere this will be equivalent to CD. Okay, so this is the diode equivalent capacitance, and in fact one can use the most practical situation. If this is my symbol of diode, then I can use in parallel the both capacitances, forward capacitance as well as reverse capacitance. So I'm marking both capacitance over here, and this will be the most appropriate symbol for a diode with the inclusion of capacitances. Okay, so this is my CT and this is my CD. So this is just because of forward bias condition, and this is reverse bias condition. Okay, so this finally is indicating my overall representation of diode with the inclusion of capacitances. So to include the effect of frequency, we must know about the diode capacitance. There are several terms, several notations we have used which are very important and must be knowing uh, for the diode, because there are so many manufacturers, number of manufacturers are available, and they will change their database. So there is an interesting topic which is termed as the diode specification. So while moving to the laboratory side, this plays very important role. We must know about the detailed specifications of diode, and for that one can use the user manual for a specific diode. So let's discuss the different component. So the first part over here is forward voltage. Forward voltage, the notation is VF. So we may have the value of Vf at some specified current and temperature. The second component is maximum forward current. Notation is If, and we have the value of this maximum forward current at some specified temperature. So as the temperature changes, the value of this If will also be changed. So this is very important parameter, the maximum forward current. In fact, in some database, it is also termed as ID max, which is the maximum forward current. And the next specification is reverse saturation current, IR. In fact, we have seen one more notation, so I'm writing that notation also, IS, which we have used most commonly. It is specified at some specific voltage and temperature. So next is reverse voltage rating. Like these first two are for forward bias, these two are related to the reverse bias of p-n junction diode. Reverse voltage rating over here, this abbreviation PIV stands for peak inverse voltage, and this PRV is also termed as peak reverse voltage, or this VBR is breakdown voltage. So these all are the same terms, peak inverse voltage, peak reverse voltage. Next I will give you the detailed definition of this PIV, peak inverse voltage, and what is the importance of this. The next specification over here is maximum power dissipation level. At a temperature it is required. In general, it is termed as PD max. At a particular temperature, we must know how much power a PN junction diode can dissipate or can handle safely. So it will termed as directly VD into ID max. As in most of the situation, value of VD is fixed. It will depends upon the type of material. So depending upon how much current can be handled by the diode will directly related to the maximum power dissipation factor. Then the next specification we have just discussed in detail, the diode capacitances, reverse recovery time. It is termed as TRR. For the switching operation, it is very important. And the last one is, so we have discussed in detail the effect of temperature on the performance of p-n junction diode. So working of diode will not be remain same if the temperature changes. So we must know all these components. So in this, the new parameter is reverse recovery time. So let us discuss this reverse recovery time in detail so that the functionality of diode for switching operation must be known. So uh, let us discuss this reverse recovery time. So in order to understand this reverse recovery time, let me draw a curve. Suppose initially my diode was in forward bias condition, and this is I forward is the current flowing, and suppose this is my transition level. I'm saying that at particular time t I want the switching, and switching is, you can check over here, my diode was on, so I want the switching from on condition to off condition. Okay, so the functionality of this is my actual curve. This black colored line is my actual curve. There is a certain time which I am writing as tt. This is my transition time, and you can see that during this particular period I am having some value of current, which is my I reverse. And there is another time which is termed as TS, and this TS is storage time. If I'm combining these two, so I will have TRR reverse recovery time, which is my TT plus TS. That means my reverse recovery time is transition time plus storage time. Reverse recovery time is my transition time plus storage time. Okay, so let's see the functioning. Initially, my diode was in on condition. At a particular time T1, there is a transition from on condition to the off condition. So what is my expectation? What is my expectation? I'm drawing over here with red color dotted line, like this is my on situation. So I must have this type of curve. So this is my expected curve. Expected curve, or I can say that my ideal curve. At transition T1, diode was on, so as there is a transition, so after this it will be off. But what is the actual condition? In the working of forward bias case, you have seen that during the forward bias the huge current will flow, and the current will flow because of the movement of the charge carriers. We have already covered in the forward bias mode, when P side of the diode is connected to the positive polarity of battery and N side is negative side to the battery, the situation is the forward bias condition, where majority carriers from P side, that is holes, cross over the junction and reach to the N side, where they become now in minority, and the reverse explanation is valid for the electrons. Majority carriers in the N side cross over the junction and reach to the P side, and now they become the minority carriers. So once there is a transition, they minority, now these minorities in the opposite side in the large quantity. So there is a requirement of some time so that these minority carriers can be revert back to their uh, original sites. So this TT is the transition time, and this T storage is the settling time required to do this particular task. So the total combination of transition time and storage time is known as the reverse recovery time. So this is very interesting parameter, reverse recovery time, and in general, this parameter have the value from few nanoseconds to 1 microseconds. So it depends upon the diode, which type of diode we are using. So just to see the performance, that how much time it will settle. So in general we can say that it is sort of delay, means after this period, after reverse recovery period, I can have the expected